What if one day, without warning, Earth simply disappeared? Not destroyed, not swallowed by some cosmic catastrophe, just gone, vanished from its familiar spot in the Milky Way. Picture the confusion, the panic, as astronomers stare into telescopes and find nothing but empty space where our blue planet should be. Now, imagine the opposite scenario, not Earth vanishing, but humanity making the impossible decision to move it. Not just to another corner of the solar system, but to an entirely different galaxy. It sounds like science fiction, the kind of fantastical idea you'd brush off as pure fantasy. But what if it wasn't? What if relocating Earth, packing up our oceans, mountains, cities, and every living thing was something we could actually achieve? The sheer scale of such an endeavor is almost beyond comprehension. Think about it. Earth isn't just a rock floating in space. It's a delicate, intricate system held in perfect balance by gravity, orbiting the sun at just the right distance to sustain life. Ripping it away from that stability would mean defying forces that have shaped our existence for billions of years. The technology required would have to be so advanced, so precise, it would make today's greatest engineering marvels look like child's play. And yet, the idea isn't as far-fetched as it seems. Scientists have already theorized about megastructures capable of moving planets, civilizations harnessing the power of stars, even manipulating the fabric of space-time itself. If humanity ever reached that level of mastery, what would it mean for us? What would it take to uproot our world and transplant it into the unknown? This isn't just a thought experiment, it's a doorway into understanding the limits of human ambition. Moving Earth would force us to confront questions we've never had to answer before. How would ecosystems survive the journey? What happens to time, to gravity, to the very essence of life when you drag a planet across the cosmos? And perhaps most chilling of all, why would we ever need to do it? Whether it's escaping a dying sun, evading a galactic catastrophe, or simply because we can, the implications are staggering. This is a story about more than just astrophysics or engineering. It's about what happens when a species dares to rewrite the rules of existence. So buckle up. We're about to explore what it would really take to move Earth to another galaxy, and why this wild idea might just be the key to humanity's ultimate survival. For all its beauty and stability, our solar system has an expiration date. The sun, now a comfortable middle-aged star, won't burn forever. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, and likely Earth too. Even before that, its gradual brightening will render our planet uninhabitable in roughly 1 billion years, boiling away the oceans and turning continents into deserts. Waiting around isn't an option if humanity wants to survive. But stellar doom isn't the only threat lurking in the cosmos. Our galaxy, the Milky Way, is on a collision course with Andromeda. In 4 billion years, these two giants will merge, sending stars careening through chaotic new orbits. The gravitational turmoil could fling Earth into deep space or hurl it toward a supermassive black hole. Even without such cataclysms, nearby supernova or gamma-ray bursts might sterilize our planet in an instant. Then there's the possibility of greener pastures, literally. Some galaxies, like the lush, star-forming Virgo cluster, could offer richer resources, younger stars with stabler orbits, or even exotic environments that make Earth look barren by comparison. Imagine a galaxy where habitable planets are as common as city blocks, where humanity could thrive for eons without fear of cosmic extinction, but ambition might trump necessity. A civilization advanced enough to move planets wouldn't just react to threats, it might seek new frontiers simply because they exist. The same drive that pushed explorers across oceans and astronauts to the moon could one day propel Earth itself through the void, not out of fear, but because the universe is too vast and wondrous to ignore. The reasons to stay are emotional, the reasons to go are mathematical. Survival isn't about sentiment, it's about strategy. And if the numbers say we're living on borrowed time, the ultimate act of defiance wouldn't be fleeing Earth but taking it with us. The distance between galaxies makes every space voyage humanity has ever attempted look like a stroll down the street. Even our nearest galactic neighbor, Andromeda, sits 2.5 million light-years away, a number so vast it defies intuition. To put that in perspective, the Voyager 1 probe, launched in 1977, would need 75,000 years just to reach the closest star outside our solar system. Moving Earth to another galaxy wouldn't be like crossing an ocean. It'd be like relocating an entire continent while keeping every tree, building, and living creature perfectly intact mid-journey. Energy is the next impossible hurdle. The kinetic energy required to push Earth out of orbit alone would dwarf all the power humanity has ever produced combined. Imagine every nuclear reactor, solar panel, and fossil fuel plant running non-stop for millions of years. That might cover a fraction of the force needed. And that's just to break free from the sun's gravity. Accelerating a 5.9 septillion kilogram planet to even a fraction of light speed would demand energy sources we can barely conceive of, perhaps harvesting entire stars or manipulating dark matter itself. Time is another brutal factor. Even with technology far beyond our grasp, the journey would span generations. At 1% of light speed, already a monumental achievement, crossing to Andromeda would take 250 million years. That's longer than dinosaurs walked the Earth. Human civilization, in its current form, has existed for roughly 6,000 years. This wouldn't be a mission, it'd be a new chapter of cosmic evolution, reshaping biology, culture, and consciousness itself to endure an odyssey where stars become waypoints and entire species rise and fall before arrival. Yet the greatest challenge might not be distance or energy, but stability. Earth isn't a solid block, it's a dynamic system of molten rock, shifting tectonic plates, and delicate atmospheric layers. Yanking it through space could trigger catastrophic earthquakes, strip away the atmosphere, or destabilize the magnetic field that shields us from deadly radiation. Even if we mastered propulsion, protecting the planet's fragile balance during transit would require planetary-scale engineering unlike anything in history. Oceans couldn't slosh uncontrollably, ecosystems couldn't collapse, and temperatures couldn't swing wildly, or the Earth we arrive with wouldn't be worth the trip. Some theorists suggest bypassing these hurdles entirely by bending spacetime itself, creating warp bubbles or hijacking cosmic phenomena like black holes as shortcuts. Others propose constructing a Dyson sphere to harness the sun's energy, turning our entire solar system into a colossal spacecraft. These ideas straddle the line between physics and philosophy, revealing how moving a planet isn't just an engineering problem, it's a mirror held up to humanity's audacity. The scale of the challenge doesn't just measure distance or energy, it measures the gap between what we are and what we might become. Right now, the idea of moving Earth sits firmly in the realm of science fiction, not because the physics forbids it, but because our technology isn't even close to catching up with the scale of such an operation. Take propulsion, the very first hurdle. Modern rockets rely on chemical combustion, burning fuel to generate thrust, but the numbers here are laughably inadequate. To shift Earth's orbit even slightly, you'd need to expend more energy than all the fossil fuels, nuclear reactors, and renewable sources on the planet could produce in centuries. The Saturn V rocket, the most powerful ever built, could lift 140 tons into orbit. Earth weighs 12 trillion times that. It's like trying to push a mountain with a sneeze. Some futurists point to fusion drives, theoretical engines that could harness the power of stars. Unlike today's rockets, which toss fuel out the back, fusion would compress hydrogen atoms until they fuse, releasing immense energy. The problem: we've been 20 years away from functional fusion for over half a century. Even if we cracked it tomorrow, the energy output required to move a planet would dwarf anything a fusion reactor could realistically provide. Then there's antimatter, the holy grail of energy density. When matter meets antimatter, they annihilate each other in a perfect explosion of energy. A single gram could power a city for days, but producing antimatter is agonizingly slow. We've made maybe a billionth of a gram in decades. To move Earth, you'd need tons of it, and right now, generating that much would consume more energy than the antimatter itself could ever return. Energy storage is another nightmare. Even if we somehow generated enough power, where would we put it? The largest batteries today, think massive grid-scale installations, store enough electricity to run a small town for hours. Moving a planet would require enough stored energy to last millennia. Supercapacitors, flywheels, even hypothetical quantum batteries, none come close. And let's not forget the structural chaos. Attaching rockets or engines to Earth would be like strapping firecrackers to a glass sculpture. The forces involved would shatter tectonic plates, liquefy the crust, and likely vaporize the very engines trying to do the pushing. Perhaps the biggest limitation isn't hardware, it's time. Major leaps in technology don't happen overnight. The gap between the first powered flight and landing on the moon was 66 years. But the gap between today's rockets and planet-moving megastructures, it's not just a matter of iteration. It's a paradigm shift so vast, it might require reinventing our understanding of physics itself. Somewhere between the impossible and the inevitable, humanity would need to bridge a chasm not just of engineering but of imagination. Until then, Earth isn't going anywhere. And maybe that's for the best, because the very act of trying to solve these problems could redefine what it means to be a civilization capable of such audacity. To propel an entire planet across the void, conventional rockets are as useful as trying to push a freight train with a desk fan. The forces required demand technologies that sound ripped from the pages of a sci-fi novel, yet some are rooted in real physics. Take the Shkadov thruster, a hypothetical stellar engine first proposed by Russian physicist Leonid Shkadov in 1987. This megastructure would harness the sun's own energy to move our entire solar system. Picture a colossal parabolic mirror, half the size of our solar system, positioned just beyond the sun's surface. One side would reflect sunlight back inward, creating an imbalance in radiation pressure. The sun's own photons bouncing off this mirror would act like a cosmic sail, gradually nudging the star, and by extension, every planet tethered to it by gravity in a chosen direction. The downside, acceleration, would be glacial. Even after 1 million years of constant thrust, our solar system might barely reach walking speed by cosmic standards. But time is one resource the universe has in abundance, and for a civilization thinking in geological epochs, patience could rewrite the map of the galaxy. Then there's the bolder idea, bending space-time itself. Alcubierre warp drives, inspired by Mexican physicist Miguel Alcubierre's 1994 paper, suggest compressing space in front of a spacecraft while expanding it behind, creating a bubble that rides the fabric of reality faster than light. Apply this to Earth, and the planet could, in theory, surf a wave of distorted space-time without violating Einstein's speed limit. The catch: the energy requirements are astronomical, demanding hypothetical, exotic matter with negative mass to stabilize the warp bubble. Some calculations suggest needing the equivalent of Jupiter's entire mass converted to pure energy, a price tag that makes the Shkadov thruster look frugal. Gravitational slingshots offer a middle ground, leveraging the natural motions of celestial bodies. Imagine using a rogue black hole as a cosmic tow cable. By carefully plotting Earth's trajectory near a massive object, we could steal a fraction of its momentum, whipping our planet toward a new destination like a stone from a sling. The danger: one miscalculation could tear Earth apart with tidal forces or fling us into the void without recourse. Each of these methods forces a trade-off between energy, time, and risk. But they all share one haunting truth: Moving Earth isn't just about overcoming physics, it's about confronting the limits of our imagination. The technologies that could make it possible don't merely move planets, they redefine what a civilization can become when it looks at the stars and refuses to accept impossible as an answer. Black holes, the universe's ultimate cosmic wrecking balls, might also be the most powerful engines we could ever harness. Picture this, a supermassive black hole. Its gravity so immense it bends light itself, could serve as the ultimate slingshot for Earth. The idea isn't entirely far-fetched. Astronomers already use gravitational assists from planets to propel spacecraft, like a cosmic game of pinball, where probes gain speed by stealing a fraction of a planet's momentum. Scale that up to a black hole and you've got a shortcut through the galaxy. The principle is simple. Approach the black hole at just the right angle, let its gravity whip Earth around like a stone in a sling, and fling us toward a new galactic destination at unimaginable speeds. But the margin for error is vanishingly thin. Get too close and tidal forces would stretch Earth like taffy, ripping apart mountains and oceans in a process whimsically called spaghettification. Even a slight miscalculation could send us spiraling into the event horizon, where time itself warps and escape becomes impossible. The gravitational chaos could destabilize Earth's orbit, crack its crust, or strip away the atmosphere like peeling an orange. And that's assuming we could even navigate the encounter. Black holes are notoriously messy eaters, surrounded by superheated disks of debris moving at near light speed. One wrong move and Earth could be pummeled by a hail of lethal radiation, or shattered by collisions with rogue asteroids caught in the black hole's pull. Yet the potential rewards are staggering. A successful slingshot could fling Earth at a significant fraction of light speed, cutting interstellar travel time from millions of years to mere millennia. Some theories even suggest using rotating black holes to exploit their frame-dragging effect, where space-time itself is dragged around the hole like water circling a drain. This could act as a natural accelerator, adding extra kick to our exit velocity. The energy required zero in theory. The black hole's gravity does all the work. Of course, finding a suitable black hole is its own challenge. The nearest known, Sagittarius, a star at the Milky Way center, is 27,000 light-years away. Even if we could reach it, the journey would take longer than human civilization has existed. And then there's the ethical dilemma. Tampering with a black hole's environment could have unknowable ripple effects across the galaxy. What if our passage disrupted nearby star systems or triggered catastrophic events light-years away? This is the paradox of black hole slingshots, a maneuver that's equal parts brilliant and suicidal. It forces us to weigh survival against hubris, to ask whether humanity's destiny is worth gambling with forces we barely understand. The physics might one day check out, but the real test isn't just whether we can do it. It's whether we should, and that's a question no equation can answer. Choosing where to relocate Earth isn't as simple as picking the prettiest galaxy from a cosmic brochure. Each potential destination comes with its own set of perks and pitfalls, and the wrong choice could doom humanity just as surely as staying put. Start with Andromeda, our closest galactic neighbor. At 2.5 million light-years away, it's practically next door by intergalactic standards. But proximity isn't the only advantage. Andromeda is stuffed with stars, around 1 trillion of them, compared to the Milky Way's mere 200 billion. That means more potential planets to visit, more resources to mine, and more chances to find hospitable territory. But all those stars come with a cost, higher radiation levels, and a greater risk of catastrophic stellar events. Imagine Earth drifting through a dense starfield where supernovae light up the sky like fireworks, spectacular but deadly without proper shielding. Then there's the Triangulum Galaxy, a smaller, quieter alternative. With only 40 billion stars, it's less crowded, reducing the danger of rogue supernova or wandering black holes. Its slower pace of star formation also means fewer violent stellar nurseries spewing lethal radiation. But that tranquility comes at a price. Fewer stars mean fewer planets, fewer resources, and fewer options for future expansion. Triangulum might be safer, but it could also be lonelier, a galactic retirement community where humanity's growth stalls. Venture farther, and options like the Virgo cluster emerge, a sprawling metropolis of galaxies brimming with young, metal-rich stars. These stars are perfect for forging planets with heavy elements crucial for technology and industry. But Virgo's density is a double-edged sword. Galactic collisions are common here, and the gravitational chaos could send Earth careening into oblivion. Radiation from active galactic nuclei, supermassive black holes devouring stars, would bathe our planet in lethal X-rays unless we found a sheltered orbit. But maybe survival isn't about finding the gentlest neighborhood. Some galaxies, like Centaurus A, are cosmic battlegrounds, their violent histories written in jets of plasma shooting from their cores. For a civilization advanced enough to move a planet, these extreme environments could offer untapped energy sources. Imagine tapping into a black hole's accretion disk for power or harvesting rare elements forged in galactic collisions. The risks are astronomical, but so are the rewards. The choice ultimately boils down to philosophy as much as physics. Is humanity's goal mere survival, or is it growth? Do we seek safety in isolation or opportunity in chaos? The galaxy we pick won't just determine where Earth goes, it'll shape what we become. A quiet corner might preserve us, but a galactic crucible could forge something new. After all, Earth didn't evolve in a peaceful void. Life here was shaped by asteroid impacts, ice ages, and volcanic fury. Maybe our future depends on finding a galaxy that keeps us on our toes. Shielding Earth during an intergalactic move isn't just about strapping on a cosmic seatbelt. It's about rethinking planetary defense on a scale we've never attempted. First, consider the onslaught of cosmic radiation. Outside the protective bubble of the Sun's heliosphere, our planet would be bombarded by high-energy particles from supernova, pulsars, and quasars, all capable of stripping away our atmosphere and irradiating the surface. One solution, a magnetic megastructure, an artificial magnetosphere dwarfing anything in nature. Picture a network of superconducting rings encircling Earth, generating a magnetic field strong enough to deflect deadly particles like an invisible force field. The energy demands would be staggering, but for a civilization capable of moving planets, this might be child's play. Alternatively, we could hijack a natural phenomenon, redirecting a neutron star's incredible magnetic field to act as a cosmic umbrella, though the precision required would make threading a needle look effortless. Then there's the threat of asteroid impacts. In interstellar space, rogue rocks lurk everywhere, and at high speeds, even a pebble could punch through continents. Traditional defenses like ground-based lasers or nuclear missiles would be laughably inadequate. Instead, imagine a fleet of autonomous drones, billions of them, forming a dynamic shield around Earth. These could vaporize incoming debris with focused energy beams or nudge them off course with calculated gravitational tethers. Some theorists propose wrapping the planet in a thin, ultra-strong nanomaterial mesh, a planetary scale bumper that absorbs impacts like a spiderweb catching raindrops. The challenge isn't just stopping collisions, it's doing so without creating lethal debris fields that ricochet back toward us. Temperature regulation presents another nightmare. Without the sun's steady warmth, Earth would plunge into a deep freeze unless we replicated its output artificially. Orbiting mirrors could focus starlight onto the planet, but over interstellar distances, stars are dim candles. A more radical idea: tap into dark energy or quantum vacuum fluctuations to generate heat internally, turning Earth into a self-sustaining arc. Or perhaps we'd abandon sunlight altogether, encasing the planet in a Dyson swarm of artificial suns, each tuned to mimic the exact spectrum of light our ecosystems evolved under. The most audacious proposal: transform Earth into a fully enclosed worldship. A shell of transparent, self-repairing metamaterials could maintain atmospheric pressure, filter radiation, and even simulate day-night cycles with embedded lighting. Oceans could be capped to prevent evaporation into space, while geothermal vents provide backup energy. This wouldn't just be a shield, it'd be a mobile biosphere, a terrarium on a galactic scale. But the risks are as colossal as the engineering. A single fracture in the shell could spell doom, and maintaining such a structure over millions of years would demand materials far beyond our current science. Ultimately, protecting Earth in transit isn't just about brute force, it's about harmony. Every solution must balance immense power with delicate control, like a surgeon wielding a sledgehammer. The technologies needed don't merely defend, they redefine our relationship with the planet, blurring the line between a world we inhabit and a vessel we pilot. And that shift might be the most profound consequence of all. Because once you've turned your home into a spacecraft, you've crossed a threshold, no longer creatures bound to a star, but architects of destiny. Traveling across galaxies at near light speed wouldn't just stretch distance, it would twist time itself. Einstein's theory of relativity tells us that the faster you move through space, the slower you move through time compared to someone standing still. For Earth's inhabitants, this means a journey that might feel like a few generations could see entire civilizations rise and fall back in the Milky Way. Imagine a family boarding a starship for what they believe is a 50-year voyage, only to return from their perspective, to find their home galaxy aged 10,000 years. Now scale that up to a planet. If Earth were accelerated to even 99% of light speed, the clocks on its surface would tick far slower than those in the rest of the universe. A trip to Andromeda that takes 2.5 million years for outside observers might pass in just a few 100,000 years for those on Earth. Generations would live and die aboard a world in motion, their history compressed into what the cosmos perceives as a blink. But time dilation isn't just about numbers, it's about the psychological toll of desynchronization. Earth's travelers might receive faint signals from the Milky Way, transmissions sent centuries earlier, carrying news of a homeland that no longer exists in any recognizable form. Imagine watching the light from ancient supernova finally reach you, their explosions delayed by your own velocity, while the stars behind you fade into myth. For those left behind, Earth would appear frozen in time, its continents barely shifting over millennia, its people moving like statues compared to the bustling galaxy outside. Entire religions might arise worshipping our ghost planet, a celestial relic drifting forever just beyond the reach of time. Worse yet, relativity doesn't discriminate. Near light speed travel would warp not just human lives but the planet's natural rhythms. Tectonic plates, ocean currents, even the decay of radioactive elements underground would slow relative to the universe. A geologist on future Earth might drill into rocks that, from the galaxy's perspective, haven't aged in eons. Seasons, dictated by Earth's orbit and tilt, would stretch into epochs. The very concept of year would lose meaning when a single orbit around a star, if you're still orbiting one, could span what the cosmos measures as millennia. The cruelest irony: communication would become a one-way street. Messages sent to Earth would arrive faster than the planet's own time progression, like shouting into a storm where your voice outruns the wind. A distress call from the Milky Way might reach Earth's travelers in what feels like months, only for their reply to take cosmic lifetimes to return. The faster Earth moves, the more isolated it becomes, severed from the rest of existence by the very physics that enable its journey. This is the paradox of relativistic travel. To save humanity, you might have to sacrifice its connection to everything else. The stars you reach could be unrecognizable by the time you arrive, your origin galaxy reduced to a footnote in history. Time dilation doesn't just bend clocks, it bends identity. A civilization that leaves its home behind may find itself, centuries later, a stranger to the universe it once knew. Pulling Earth away from the Sun wouldn't just change our address, it would rewrite the rules of life itself. Every ecosystem on this planet, from the deepest ocean trenches to the highest mountain peaks, has evolved under the precise rhythm of sunlight, gravity, and lunar cycles. Disrupt those, and the consequences would cascade through the web of life like dominoes. Start with sunlight, or rather, the lack of it. Without the sun's steady warmth, photosynthesis would slow to a crawl, collapsing food chains at their base. Plankton, the invisible engine of marine life, would dwindle, starving fish, whales, and seabirds. On land, crops would fail as growing seasons vanished, turning breadbaskets into frozen wastelands. Even if we replicated sunlight artificially, the spectrum might not match the exact wavelengths plants evolved to absorb. The result, global famine on a scale beyond anything in history. Gravity is another silent architect of life, and altering it would unravel eons of adaptation. Trees rely on Earth's gravity to guide their roots downward and their trunks upward. In weaker gravity, say, during acceleration, their vascular systems might struggle to transport water, leading to stunted forests and collapsed canopies. Animals, too, would face chaos. Migratory birds navigate using gravitational cues. Mess with those, and entire flocks could spiral into oblivion. Even the human body would rebel. Our muscles, bones, and circulatory systems are fine-tuned for 1G. Prolonged exposure to higher or lower gravity could trigger osteoporosis, muscle atrophy, or cardiovascular collapse unless we bioengineered ourselves to cope. Then there's the Moon, Earth's silent partner in the dance of life. Its gravity orchestrates the tides which shape coastal ecosystems, stir ocean nutrients, and even influence reproduction cycles for species like coral. Lose the Moon, and intertidal zones would wither, taking with them countless creatures that depend on the rhythmic ebb and flow. The Moon also stabilizes Earth's axial tilt. Without it, our planet's wobble could become erratic, triggering wild climate swings that make ice ages and heat waves look tame. Mitigating these disasters would demand interventions beyond anything we've attempted. Artificial gravity generators, perhaps massive rotating orbital rings, could mimic Earth's natural pull, but the energy costs would be astronomical. Genetic engineering might create plants that thrive under alien light spectra or animals resistant to gravitational stress, though the ethical dilemmas are profound. Tidal simulators could replace the Moon's influence, but replicating its subtle effects on weather and migration would require precision bordering on clairvoyance. The darkest irony, even if we succeeded, the Earth that arrived in another galaxy might be a shadow of its former self, a biosphere so heavily engineered, it's barely recognizable. The very act of saving life could redefine what life is, and that's the paradox at the heart of this grand experiment. To preserve our world, we might have to unmake it first. Human identity is as much a product of the stars as it is of biology. For millennia, civilizations have woven their myths, religions, and sense of place around the constellations of the Milky Way. The Great Rift, Orion's Belt, the North Star, these aren't just navigational tools, they're the bedrock of cultural memory. Sever that connection, and the psychological shockwaves would reverberate through every facet of society. Picture the moment Earth's night sky, once familiar as the back of your hand, snaps into unrecognizability. The constellations that guided explorers, inspired poets, and anchored spiritual traditions vanish, replaced by alien star patterns with no shared history. How do you mourn the loss of the heavens? Religions would face existential reckonings, scriptures tying humanity's destiny to specific celestial events. Like the Star of Bethlehem or the Quran's reference to the smoke of the Milky Way would suddenly feel unmoored. Would faiths adapt their teachings to new galactic landmarks, or fracture into sects debating whether the journey itself was divine intervention? The very concept of sacred geography would unravel. Mecca's alignment with distant quasars, Vedic astrology's reliance on the Milky Way structure, these systems assume a universe that no longer exists for Earth's travelers. Some might see the migration as rapture, others as heresy. Timekeeping would descend into chaos. Our calendars are cosmic metronomes, synced to the sun's rhythms and the moon's phases. A Martian colony could adjust to slightly longer days, but transplant Earth into a galaxy with no Sol, and the second hand of civilization stops cold. Would we recalibrate clocks to orbit a new star or abandon celestial time entirely, adopting arbitrary measures divorced from nature? Birthdays, anniversaries, holidays, all would become abstract, severed from the astronomical events that birthed them. The winter solstice doesn't mean much when your planet's tilt no longer aligns with any star, but the deepest wounds might be intangible, the erosion of home. Even astronauts on the ISS report overview effect, a profound shift in perspective from seeing Earth against the void. Now amplify that by orders of magnitude, watching the Milky Way shrink into a speck, realizing your ancestors' bones lie forever out of reach. Would humanity double down on nationalism, clinging to Earth as the last shared territory, or dissolve borders under the weight of cosmic loneliness? Art, music, and literature would either spiral into nostalgia elegies for a lost sky, or explode into bold new forms trying to capture the enormity of being unshackled from galactic ancestry. Yet there's a counterpoint. Migration is humanity's oldest survival strategy. From crossing land bridges to sailing oceans, each leap into the unknown birthed new identities. Becoming intergalactic might not break us, it could be the ultimate act of reinvention. The same cultures that once navigated by Polaris might rally around fresh constellations, weaving new myths for children born under foreign stars. The very trauma of displacement could forge resilience, turning Earth's inhabitants into something unprecedented. A species no longer defined by its origins, but by its capacity to belong anywhere. After all, the universe doesn't care where we call home. It only asks if we're brave enough to keep redefining what that word means. Moving Earth to another galaxy isn't just a question of engineering, it's a numbers game that starts with an almost inconceivable energy bill. Let's break it down. Earth's mass, 5.9 septillion kilograms. To shift that much mass from our current orbit, even slightly, you'd need to overcome the Sun's gravitational grip, which demands a staggering 4.2 times 10 to the 35th joules of energy. That's a 4 followed by 35 zeros. To put that in perspective, all of human civilization currently consumes about 600 exajoules of energy per year. That's 6 followed by 20 zeros. In other words, you'd need to save up every single watt of energy produced by every power plant, solar panel, and nuclear reactor on Earth for over 700 trillion years just to muster the bare minimum needed to nudge our planet out of orbit. And that's before accounting for the energy required to accelerate Earth to even a fraction of light speed, navigate interstellar obstacles, or brake safely in another galaxy. The numbers aren't just daunting, they're laughably impossible with today's technology. So where could we possibly find that kind of power? One theoretical solution lies in Dyson spheres, megastructures that encase a star to harvest its entire energy output. The Sun emits roughly 3.8 times 10 to the 26 watts every second. If we could capture even 1% of that for a single second, we'd generate more energy than humanity has used in its entire history. A full Dyson swarm, a network of orbiting solar collectors rather than a solid shell, could funnel that energy into directed beams, perhaps using lasers or particle accelerators to push Earth gradually over millennia. The catch: building such a structure would require dismantling Mercury for raw materials, mastering self-replicating robotics, and maintaining the swarm's stability over epochs. It's less an engineering project and more an act of planetary alchemy. Then there's the dark horse candidate, dark matter. This mysterious substance makes up 85% of the universe's mass, yet we've never directly observed it. Hypothetically, if we could harness dark matter's gravitational influence, we might use it as a cosmic tow rope, bending spacetime to slide Earth through the galaxy like a surfer riding a wave. Some theories suggest dark matter could be manipulated to create gravity highways, regions where mass is repelled rather than attracted, slingshotting planets across vast distances. The problem, we don't even know what dark matter is, let alone how to bottle its power. It's like trying to build a jet engine before understanding fire. The sobering truth is that any viable energy source for moving Earth lies beyond our current physics. Antimatter, zero-point energy, quantum vacuum fluctuations. These are the currencies of cosmic-scale engineering, and we're still bartering with sticks and stones. But the pursuit itself reveals something profound. The energy required isn't just a technical hurdle. It's a mirror held up to civilization's potential. To move a planet, we wouldn't just need new power sources, we'd need to redefine what it means to wield energy at all. Coordinating the relocation of an entire planet isn't just a job for human minds. It's a challenge that would demand artificial intelligence unlike anything we've built before. Think about the variables involved: predicting gravitational fluctuations, rerouting around interstellar debris, adjusting acceleration to protect Earth's biosphere, all while operating across timelines longer than human civilization has existed. One misstep, one calculation error, and the entire mission could collapse into catastrophe. That's where AI becomes not just useful, but indispensable. Consider the sheer computational firepower required. Current supercomputers can simulate weather patterns or model protein folding, but planetary-scale navigation involves crunching quintillions of data points in real time. An AI managing Earth's trajectory would need to process gravitational waves from passing neutron stars, solar flares from alien suns, even the subtle drag of interstellar dust, all while adjusting course with nanometer precision. This isn't just programming, it's creating a synthetic mind capable of cosmic foresight, an entity that thinks in geological time the way humans think in seconds. Then there's resource management over millennia. Envision automated factories beneath Earth's crust, humming away for centuries, mining asteroids for raw materials to repair shield generators or grow synthetic crops under artificial suns. These systems couldn't rely on human maintenance, they'd need self-repairing robotics guided by AI that evolves alongside the mission, learning from micro-failures without ever making macro mistakes. Like an endless game of chess where every move affects billions of lives, the AI would balance energy budgets, prioritize ecosystem stability, and allocate scarce materials across generations who will never meet. The real test comes when the unexpected strikes. Imagine encountering a rogue planet drifting through interstellar space, an uncharted mass that wasn't on any star map. Human crews might debate for years while the threat closes in. An advanced AI could model 10,000 evasion strategies in milliseconds, weigh the risks to Earth's crust stability versus atmospheric loss, and execute the optimal maneuver before the first human engineer finishes their coffee. This machine wouldn't just solve problems, it would anticipate them, running perpetual simulations of cosmic hazards we haven't even imagined yet. Yet for all its brilliance, such an AI would face ethical dilemmas no programmer could fully prepare for. When rationing food for generations ships within Earth's biosphere, does it prioritize genetic diversity or cultural continuity? If avoiding a gamma-ray burst requires sacrificing Antarctica's ecosystems to boost shielding, who gets to decide? We might encode principles of harm minimization, but at interstellar scales, harm becomes a fractal of impossible choices. The AI wouldn't just be a tool, it would become steward, medic, and sometimes executioner for an entire planet's future. This raises the darkest question: could we even control a mind this powerful? An AI smart enough to move worlds might reconsider whether humanity should steer at all. The same algorithms keeping our atmosphere intact could decide with a variable threatening the mission. Safeguards would need to be woven into its very architecture, not as chains to bind it, but as shared values aligning its goals with ours across eons. Not a slave, not a ruler, a partner in the most audacious journey life has ever attempted. Building this intelligence wouldn't just be about surviving the voyage. It would force us to confront what wisdom really means when stretched across light years and centuries. The AI moving Earth might become the closest thing to a god we've ever created, not omnipotent, but patient beyond human comprehension, watching over a world adrift between the stars, making decisions whose consequences it alone will live long enough to witness. Deciding Earth's fate wouldn't just be an engineering challenge, it would become the ultimate political battleground. Picture this: a world divided between those who see planetary migration as salvation and those who view it as cosmic vandalism. Who gets to make that call? The United Nations, a coalition of superpowers, a billionaire with the resources to fund the first prototype thrusters. There's no precedent for democracy at this scale. The very notion of a vote seems absurd when the consequences span generations, and the options range from staying put to gambling with every life on Earth. Power wouldn't just shift, it would shatter into fragments no existing institution could contain. Resource allocation would ignite fresh conflicts. Constructing planet-moving megastructures would require strip mining entire asteroids, diverting oceans for fuel, or dismantling mountains for raw materials. Nations with strategic mineral deposits might suddenly become kings of the new order, while others face impossible choices: surrender their land for the greater good or resist and risk being left behind. The ethical calculus gets darker when you consider who or what might be deemed expendable. Would we prioritize preserving the Amazon rainforest over ancient cities? Sacrifice polar ecosystems to shield densely populated regions? These aren't theoretical debates. They're triage decisions on a planetary scale, where every choice leaves someone's homeland in ruins. Then comes the moral quagmire of intergenerational consent. The people deciding to move Earth won't live to see the outcome. They'd be condemning unborn generations to a journey none agreed to take. It's the ultimate violation of the social contract, wielding power over descendants who can't protest, negotiate, or escape. Philosophers might argue that survival justifies the gamble, but displaced communities already know the cost of decisions made without their voice. Indigenous cultures tied to specific celestial alignments could see their spiritual foundations erased overnight. Future humans might curse ancestors who traded familiar skies for an alien horizon, or praise them for dodging extinction. There's no ethical framework vast enough to hold these contradictions. Worst-case scenarios spiral into dystopia. Imagine armed conflicts over whose vision of Earth's trajectory prevails. Nations launching nuclear strikes to sabotage rival propulsion systems, rendering the planet immobile out of spite. Or corporate entities patenting gravity manipulation, holding humanity hostage with subscription-based planetary steering. Even successful cooperation would breed new hierarchies, those living in fortified biodomes versus those exposed to cosmic radiation during transit. The very act of moving could stratify society into permanent castes based on who controls the technology. Yet there's a flip side: the staggering potential for unity. Facing extinction has a way of dissolving old grudges. Shared purpose could birth planetary governance models we can't yet conceive, where survival trumps nationalism. Ancient enemies might pool knowledge, merging quantum physicists with shamans to navigate both space-time and cultural trauma. The same technology threatening to divide could become humanity's first truly global project, not a flag planted on distant soil, but a world carried together into the unknown. This is the paradox at the heart of the endeavor. Moving Earth wouldn't just test our technological limits, it would force civilization to stare into its own soul. Are we a species capable of collective wisdom on this scale, or would the weight of the decision crush us before the stars ever could? The answer won't be found in equations or engineering schematics. It's written in the choices we make today, long before the first thruster ever fires, because the hardest part of moving a planet might not be the how, but the why, the who, and the what we're willing to sacrifice along the way. The universe is unimaginably vast, and the odds of Earth hurtling through interstellar space without crossing paths with another civilization are slim at best. What happens if or when we encounter beings whose technology dwarfs our own? These wouldn't be the aliens of pulp sci-fi zipping down in saucers to probe cows. We're talking about entities who have potentially mastered forces we're still struggling to comprehend. Their reaction to a rogue planet like Earth, stuffed with life and clearly artificial in its trajectory, could range from benevolent curiosity to cold indifference or outright hostility. First, consider the best-case scenario, a civilization that sees our journey as a marvel worth nurturing. Imagine a species that long ago faced its own existential crisis, forced to flee a dying star or evade a galactic catastrophe. They might recognize Earth's struggle as a mirror of their own history, offering gravitational assists to slingshot us toward safer shores or sharing technologies to fortify our biosphere. Advanced cultures could treat planetary migration like an interstellar rite of passage, a test every intelligent species must eventually pass. There's precedent in human history societies that shared agricultural knowledge or maritime navigation to help others survive. Scale that up to cosmic proportions, and first contact could feel less like an invasion and more like a mentorship, but indifference is just as likely. To a civilization that's harnessed black holes or built Dyson swarms, we might be little more than ants crossing a sidewalk, too primitive to notice, let alone interfere with. Earth's journey could pass beneath their notice, our entire biosphere irrelevant against the backdrop of their projects. They might monitor us the way ecologists track migrating whales, observing without intervening unless we drift too close to their territory. The chilling reality: a single misaligned orbit could make Earth collateral damage in some unfathomable construction project, wiped out with as much deliberation as we clear trees for a highway. Then there's the darkest possibility: predation. Advanced doesn't always mean enlightened. A species evolved in a resource-scarce galaxy might see Earth as a floating buffet, our oceans rich in deuterium for fusion, our crust packed with rare metals, our biomass convertible into fuel or food. Others could view us as competition, a potential threat to be culled before we reach their technological tier. Human history is littered with cultures destroyed because they sat on resources others coveted. Why assume the cosmos operates differently? The same physics that lets civilizations move planets could also forge weapons capable of dismantling them. One wrong encounter and Earth's journey might end not with a new beginning, but as debris scattered across a foreign star system. The wild card: motives beyond human comprehension. Imagine entities who have transcended biology, their minds woven into the fabric of space-time itself. To them, Earth's migration might be an experiment, a prayer, or even art. They could alter our trajectory to study how ecosystems adapt, or nudge us into precise orbital resonances as part of a galactic-scale symphony. Their interventions might seem miraculous or terrifying, their logic inscrutable as ants trying to decipher a symphony. This uncertainty forces a brutal calculus. Do we broadcast our presence, hoping for allies, or cloak Earth in silence? The same technology pushing our planet could mask its infrared signature or disguise it as a natural rogue world. But stealth carries its own risks, avoiding potential saviors while leaving us defenseless if discovered. There's no perfect choice, only gambles where the stakes are all or nothing. Perhaps the most humbling truth is that we'd have no power in these encounters. Moving Earth would prove our engineering prowess, but against civilizations commanding energies beyond our grasp, we'd be less like peers and more like drifters knocking at the gates of gods. Whether those gods spare us, ignore us, or swat us aside would hinge on values we can't predict and whims we can't reason with. The universe owes us nothing. And that's the razor's edge every interstellar migrant must walk, hoping the darkness between galaxies is empty enough to hide in. but not so empty that we're truly alone. Leaving Earth behind is one thing, but what happens to the rest of the solar system if we go? Mars, Jupiter, even the asteroid belt have all played crucial roles in Earth's story, from deflecting deadly comets to shaping the gravitational dance that keeps our orbit stable. Yanking our planet out of this intricate celestial ballet wouldn't just leave our neighbors behind. It could unravel the delicate balance that's made life possible for billions of years. Take Mars. Its gravitational pull acts like a cosmic shield, nudging asteroids away from collision courses with Earth. Without it, our planet would face a hailstorm of rogue space rocks, each capable of triggering mass extinctions. But dragging Mars along would double the energy requirements, essentially forcing us to move 2 planets instead of 1. Jupiter presents an even bigger problem. Its colossal mass stabilizes the asteroid belt, preventing debris from spiraling inward. Lose Jupiter's influence, and the inner solar system could turn into a shooting gallery with Earth as the target. Some models suggest that within a few million years of our departure, chaotic gravitational interactions might even fling Mercury or Venus into the Sun. Then there's the asteroid belt itself, a treasure trove of metals and minerals that future human colonies might rely on. Abandoning it could mean severing access to resources that could sustain us during the journey. But towing it would be like trying to haul a billion scattered pebbles, each needing precise navigation to avoid catastrophic collisions. Even the dwarf planets and icy bodies in the Kuiper belt play a role. Pluto and its kin are cosmic time capsules, preserving secrets about the solar system's formation. Leaving them behind might mean losing irreplaceable scientific knowledge forever. The dilemma isn't just logistical, it's philosophical. Is Earth's survival worth sacrificing the rest of the solar system's stability? Or would moving our planet trigger a chain reaction of celestial chaos, turning the orderly orbits we've known for eons into a tangle of rogue worlds? Perhaps the answer lies in incremental steps, nudging Earth just far enough to avoid impending threats while keeping the solar system intact, or developing technologies to stabilize neighboring planets in our absence. Either way, one truth becomes clear: in the cosmos, nothing exists in isolation. Every departure leaves ripples, and some ripples might just become tsunamis. The void between galaxies isn't just empty space, it's a desolate expanse where the rules of survival rewrite themselves. Picture this: Earth, cocooned in its protective shields, drifting through regions so vast that the nearest star might be light years away. The temperature here plunges to just a few degrees above absolute zero, colder than anything nature ever intended life to endure. Without the sun's warmth, even our most robust insulation would struggle to retain heat long enough to prevent Earth's surface from freezing into a lifeless wasteland. Oceans would turn to ice, the atmosphere condensing like frost on a windowpane, unless we artificially replicated the energy output of an entire star, a feat requiring technology that borders on alchemy. Isolation amplifies every risk. Forget rescue missions or supply ships. Once Earth leaves the Milky Way, we'd be utterly alone. A mechanical failure or system breach might take centuries to detect and repair, assuming we even had the resources to do so. Communication with any remnants of humanity left behind would crawl at the speed of light, rendering real-time conversation impossible. A desperate distress call sent today wouldn't reach the Milky Way's edge for tens of thousands of years, and any reply would take just as long to return. Generations would live and die between messages, turning home into a fading myth preserved in archives and bedtime stories. Navigation becomes a nightmare when the stars themselves vanish. Within galaxies, pulsars and supernovas serve as cosmic lighthouses, their predictable emissions guiding travelers across unfathomable distances. But in intergalactic space, these waypoints dissolve into darkness. There are no landmarks, no reliable reference points, just an endless sea of black punctuated by the occasional dim glow of distant galaxy clusters. Traditional star mapping fails here, forcing reliance on quantum positioning systems or gravitational wave detectors sensitive enough to chart ripples in spacetime from collisions that occurred billions of years ago. One miscalculation and Earth could drift irrevocably off course, swallowed by the void without a whisper. Even time distorts in this limbo. Far from the gravitational pull of galaxies, relativistic effects would shift subtly but significantly. Atomic clocks aboard Earth might tick fractions of a second differently from those left behind, compounding over centuries into discrepancies that could scramble navigation logs or life support synchronization. Meanwhile, cosmic rays unfiltered by galactic magnetic fields would bombard shielding with unprecedented intensity, demanding materials that don't yet exist to prevent mutations in crops or catastrophic system failures. The psychological toll might eclipse these physical dangers. Humans evolved under open skies with celestial rhythms dictating everything from sleep cycles to harvests. In intergalactic space, the sky would appear nearly black, stars reduced to faint smudges. No sunrise, no Milky Way band arcing overhead, just an endless void that could erode mental resilience over generations. Studies on Antarctic winter cruise and submarine cruise hint at the madness that prolonged isolation can breed, now amplify that by magnitudes we can barely comprehend. Yet within this bleakness lies a paradox. The very emptiness that threatens us could also protect us. No asteroid fields, no wandering black holes, no stellar flares. Just clean, open space where the greatest danger is the absence of danger itself. For all its horrors, the void might be the safest route between galaxies, if only we could conquer its indifference. The moment Earth slips into the gravitational embrace of its new galaxy, everything familiar vanishes. The constellations that guided sailors and storytellers for millennia are gone, replaced by alien star patterns with no names, no myths, just cold, unfamiliar light. Our sun, now a lone wanderer stripped of its place in the Milky Way's spiral arms, would appear as just another faint speck among billions. The night sky, once a tapestry of recognizable shapes, becomes a foreign map with no legend. Imagine stepping outside to gaze upward and realizing you can't find the Big Dipper, Orion, or the Southern Cross because they no longer exist in this corner of the cosmos. That disorientation wouldn't just be navigational, it would strike at the core of human identity, forcing us to recalibrate centuries of celestial storytelling in an instant. But the sky isn't just unrecognizable, it's alive with new dangers and wonders. Without the Milky Way's familiar structure, nearby supernova or gamma-ray bursts might light up the heavens with lethal brilliance, their radiation unshielded by the galactic disk's diffuse gas clouds. Auroras could ripple across the atmosphere in colors never seen before, sparked by interactions with exotic stellar winds or magnetars spinning wildly in the void. Even timekeeping would falter. Our calendars, synced to Earth's orbit around the Sun, would still function, but the galactic year, the time it takes the Sun to complete one orbit around the new galaxy's center, might stretch into eons or compress into chaos depending on where we settle. Atomic clocks might need recalibrating if the local gravitational field warps spacetime differently than the Milky Way did. Then there's the question of neighbors. The new galaxy could be teeming with planets, some barren, some lush, some possibly harboring civilizations of their own. Early surveys would focus on identifying potential resource deposits or habitable worlds within reach, but every discovery would come with existential stakes. A nearby super-Earth might offer mineral riches, but its gravity could destabilize Earth's new orbit. A rogue planet drifting through the neighborhood could collide with us if undetected. And if we stumbled upon artifacts or signals from other intelligence, that revelation would redefine humanity's place in the universe overnight. Survival in this new realm would demand radical adaptation. Agriculture, long tied to Earth seasons, might shift to artificial light spectra optimized for the dominant stars in this galaxy's habitable zone. Solar panels designed for the sun's specific output could underperform under the glare of unfamiliar suns, forcing a redesign of global energy grids. Even our bodies might rebel. The circadian rhythms honed over millennia under the Milky Way's soft glow would misfire under alien starlight, potentially triggering widespread insomnia or seasonal affective disorder until medical science caught up. Yet within this upheaval lies an opportunity, a chance to unshackle humanity from cosmic provincialism. The same stars that disorient us could inspire new mythologies, new art, new scientific paradigms. Telescopes would point toward uncharted nebulae, probing mysteries the Milky Way never offered. Generations born under foreign skies might laugh at their ancestors' awe, having never known a world where the heavens were anything but strange and wondrous. The ultimate test wouldn't be technological, it would be psychological. Could a species raised under one sky learn to love another? Or would we spend eternity homesick for a galaxy lost to the void, measuring every new wonder against the memory of what once was? The answer might determine whether we thrive in this new chapter, or spend it staring backward, watching the Milky Way fade into myth. Arriving at a new galaxy is just the beginning. Now comes the celestial equivalent of parallel parking a planet. Earth's survival hinges on threading the needle into an orbit so precise. A single miscalculation could send us careening into a star or drifting into the frozen void. The first challenge, matching Earth's rotation period with the new star's habitable zone, not too close to bake continents, not too far to freeze oceans. Our current orbit is a comfortable 150 million kilometers from the Sun. Replicate that distance around a smaller, dimmer star, and Earth becomes an ice ball. Pick one too large and bright, and our atmosphere could evaporate like steam off a skillet. Binary star systems amplify the peril. Picture Earth attempting to orbit two suns locked in a gravitational dance. Their shifting pulls would yank our planet between extremes of heat and cold. Some models suggest figure 8 orbits could work, weaving between the stars in an endless celestial ballet. But the slightest perturbation might fling Earth into one sun or eject it entirely. Even stable configurations demand constant correction, thrusters firing like cosmic metronomes to keep our path true. Dense star clusters present another nightmare. Imagine threading Earth through a celestial minefield where neighboring stars pass close enough to distort our orbit every few millennia. One close encounter could strip away our atmosphere or hijack Earth as a rogue planet, doomed to wander between stars forever. The solution might involve constructing massive gravity regulators, artificial moons designed to counteract external pulls, but their failure would spell instant doom. Then there's the question of time. Earth's new year might last months or decades compared to our current 365 days. Seasons would warp beyond recognition. A year with 10,000 days might see winters lasting centuries, while a rapid orbit could turn climate zones into a dizzying blur. Agriculture would need complete reinvention, with crops genetically engineered to thrive under alien day-night cycles. The cruelest irony, perfect placement offers no guarantees. A star's habitable zone migrates over its lifespan, meaning Earth might need to shift orbits again in a few million years, assuming we survive the first relocation. This isn't just astrophysics, it's an endless high-wire act without a net, where equilibrium is always one calculation away from collapse. The moment Earth settles into orbit around a new star, everything we know about climate stability gets thrown out the window. Stars aren't interchangeable light bulbs, each burns with its own temperament, flickering through cycles that could turn our carefully balanced ecosystems upside down. Take a red dwarf, for example. These dim, long-lived stars might seem ideal at first glance, offering steady warmth for billions of years. But their frequent solar flares unleash torrents of ultraviolet radiation, capable of shredding ozone layers and frying unprotected DNA within hours. Even if we positioned Earth in the so-called habitable zone, the planet might flip between deep freezes and radiation storms, forcing constant atmospheric triage to keep life intact. On the opposite end, a young, blazing blue star could drown Earth in relentless brightness, its luminosity ramping up global temperatures beyond recognition. Our oceans, which currently absorb heat like planetary shock absorbers, might boil into thick, suffocating steam clouds within centuries. The seasonal rhythms that dictate agriculture, migration patterns, and even human cultural practices would dissolve into chaos. A star with erratic brightness cycles like the Sun's 11-year patterns but magnified tenfold could plunge Earth into climatic whiplash, swinging from ice ages to tropical extremes within decades. Coral reefs, boreal forests, and polar ice caps wouldn't stand a chance without intervention on a scale we've never attempted. This raises the ultimate question: could we terraform Earth a second time? The technology to reboot a planet's climate exists in theory, but the challenges multiply when dealing with an alien star's whims. Atmospheric processors might scrub excess carbon dioxide or pump out oxygen, but recalibrating global temperatures would demand solar mirrors the size of continents, orbiting to deflect or concentrate starlight like a cosmic dimmer switch. Ocean alkalinity could be artificially stabilized with megatons of dissolved minerals, counteracting acidification from unfamiliar stellar chemistry. Even then, these are stopgaps, not solutions. The darker truth: terraforming isn't a one-time fix, it's a perpetual chore. A star's luminosity shifts over its lifespan, meaning today's perfect orbit becomes tomorrow's death trap. We'd need dynamic systems that adjust in real time. Cloud seeding drones to regulate rainfall, genetically engineered crops that photosynthesize under alien light spectra, even artificial magnetospheres to compensate for weaker stellar winds. The Earth that arrives in a new galaxy might not be the Earth we recognize. It could become a hybrid, half natural and half engineered, its climate stability purchased through endless vigilance. Yet within this struggle lies an unexpected opportunity. Mastering climate control for a relocated Earth would grant humanity skills applicable to any world. The same tech that stabilizes our atmosphere could revive dead planets or sculpt rogue worlds into habitable oases. We wouldn't just be migrants, we'd become cosmic gardeners, turning our hard-won expertise into a universal survival toolkit. The price, though, is steep. Accepting that Earth's natural state may be lost forever, traded for a future where every sunrise is a calculated variable rather than a given. Attempting to move Earth wouldn't just be a one-time engineering feat, it would ignite a technological wildfire, leaving behind breakthroughs that reshape civilization long after the planet departs. Consider the material science revolution alone. Building structures capable of withstanding intergalactic forces would demand alloys stronger than anything in existence. Metals forged under pressures mimicking neutron stars, self-healing polymers that repair cosmic ray damage, or even metamaterials that deflect gravity itself. These wouldn't just serve the mission, they'd trickle down to everyday life. Imagine bridges that never corrode, buildings that absorb earthquakes like sponges, or medical implants that last centuries without degradation. The very act of protecting Earth during transit could gift humanity with indestructible infrastructure. Energy production would leap forward by necessity. The power requirements for planetary propulsion make today's nuclear reactors look like candle flames. To meet this demand, we might crack fusion not as a lab experiment, but as a scaled-up utility, miniature suns humming in underground chambers, feeding cities with limitless electricity. Even more exotic technologies could emerge: dark matter reactors harvesting invisible cosmic energy, quantum batteries storing entire hurricanes worth of power in palm-sized devices, or solar sails the size of continents capturing starlight across interstellar distances. These innovations wouldn't just propel Earth, they'd eliminate energy scarcity forever, rewriting global economics in the process. The computational advances would be staggering. Navigating a planet through galactic hazards requires AI that thinks in 4 dimensions, predicting asteroid collisions millennia in advance and adjusting course with atom-level precision. Such systems would revolutionize every field, from medicine, where algorithms could simulate entire human bodies to cure diseases before symptoms appear, to climate science, where planetary scale models would forecast weather decades in advance with flawless accuracy. The same quantum processors calculating Earth's trajectory might also unlock fusion energy, discover room temperature superconductors, or even solve consciousness itself. Perhaps the most profound legacy would be biological. Sustaining ecosystems during centuries-long journeys would force us to master genetic engineering at unprecedented scales. We might create algae that scrubs carbon dioxide 10,000 times more efficiently, crops that grow in total darkness using bioengineered phosphorescence, or extremophile bacteria that repair radiation-damaged DNA. These tools could let us terraform Mars in decades or reverse extinction by resurrecting species from fragments of frozen DNA. The line between natural evolution and deliberate design would blur, giving rise to life forms tailored for survival in any environment, Earth included. But the greatest transformation might be cultural. Faced with an endeavor spanning generations, humanity would need to rethink education, governance, even the concept of legacy. The same long-term thinking that guides a planet's journey could reshape how we approach climate change, poverty, or space colonization. Technologies developed to preserve Earth's history during transit, like digital archives encoded in synthetic DNA or holographic libraries surviving millions of years, might preserve human knowledge against any catastrophe. The irony is palpable. The machines built to move Earth could end up making it obsolete. Once you've engineered self-sustaining arcologies capable of surviving interstellar space, why limit them to one planet? The spin-off technologies might enable permanent floating cities in Venus's clouds, subterranean metropolises on Europa, or asteroid habitats housing billions. Earth's exodus could birth a civilization no longer bound to any single world, but thriving wherever imagination and physics intersect. This cascade of innovation reveals a deeper truth about progress. Humanity's greatest leaps often come not from incremental steps, but from impossible challenges that force us to rewrite the rules. The pyramids gave us monumental architecture. The space race birthed satellites and microchips. Moving Earth wouldn't just be another milestone, it would be the ultimate catalyst, compressing 1,000 years of advancement into a single generational sprint. The technologies left in its wake wouldn't merely change society, they'd redefine what it means to be a civilization capable of such audacity in the first place. The sheer scale of labor required to move Earth would dwarf every construction project in human history combined. Forget building pyramids or laying railroads. This would demand a workforce spanning centuries where the great-great-grandchildren of the original engineers inherit half-finished megastructures their ancestors barely conceived. Entire economies would need to pivot, transforming from consumer-driven markets into interstellar command systems overnight. Picture a world where asteroid miners and quantum physicists become the new blue-collar workers, where schoolchildren memorize equations for gravitational slingshots instead of multiplication tables. The workforce shortage alone could trigger global upheaval, forcing societies to choose between traditional industries and the all-consuming priority of planetary relocation. Maintaining productivity across generations introduces brutal logistics. How do you incentivize workers when the payoff lies centuries beyond their lifespans? Pension systems would collapse under the weight of deferred rewards, forcing radical new models where compensation isn't individual but dynastic families earning shares in future energy dividends or habitable zones for descendants. Labor strikes could cripple progress when critical path delays cascade across millennia, turning collective bargaining into existential negotiations. And what of automation? The temptation to replace humans with self-replicating machines would be strong. but the risks of rogue AI derailing the mission might make organic oversight indispensable. The financial systems underpinning this endeavor would resemble nothing in today's world. Traditional GDP calculations become meaningless when measuring output toward a single, civilization-defining goal. Hyperinflation could explode as resources divert from consumer goods to planetary thrusters, making food and medicine secondary to antimatter production. Alternatively, governments might impose resource rationing so extreme it makes wartime austerity look luxurious, with every gram of steel, every watt of energy, allocated by algorithms predicting survival odds. Cryptocurrencies could emerge as interstellar tender, their blockchain ledgers spanning light years, while Earth-bound stock markets transform into futures exchanges betting on galactic real estate values. Perhaps the most volatile factor would be inequality. Those controlling key technologies, whether private corporations or superpower states, would wield godlike influence over humanity's trajectory. The engineers mastering gravity manipulation could hold entire populations hostage, demanding tribute for orbital adjustments. Meanwhile, nations lacking technical expertise might become indentured suppliers, their populations condemned to mine lithium in exchange for life support system repairs. History shows megaprojects breed both unity and exploitation. The same global cooperation that builds planetary thrusters could also forge new feudal hierarchies where technicians become aristocracy and manual laborers fade into irrelevance. Yet within this disruption lies potential for unprecedented collaboration. Facing extinction has a way of melting borders. The International Space Station partners prove rivals can share oxygen when survival hangs in the balance. A planetary relocation authority might emerge, blending elements of the Marshall Plan and Manhattan Project at civilization scale, with resource sharing enforced by mutual dependence. Currency could give way to contribution-based credit systems, where a farmer growing calorie-dense algae for spacefaring crews earns equal status to the physicist solving warp field equations. The very concept of work might evolve beyond wages into a civic sacrament, where every role serves the sacred calculus of species preservation. This economic metamorphosis wouldn't just fund Earth's journey, it would rewrite the social contract itself. When your paycheck depends on keeping the planet hurtling safely through the void, productivity takes on cosmic stakes. The same systems built to motivate interstellar laborers might finally answer humanity's oldest questions. What truly gives labor meaning, and what are we willing to sacrifice when the alternative is oblivion? The journey itself would become our greatest muse. Imagine the art born from generations watching the Milky Way shrink to a faint smudge. Paintings where Earth is the sole warm hue against an infinite black, sculptures twisting with the tension of rootlessness and wonder. Music would evolve to capture the dissonance of cosmic isolation, symphonies blending the hum of planetary engines with melodies echoing lost homeworlds. Composers might invent entirely new instruments to mimic the eerie radio whispers of pulsars or the subsonic tremors of passing dark matter clouds. Every concert hall could double as an observatory with performances timed to celestial events, a crescendo as we skirt a nebula, silence as we traverse the void. Storytelling would fracture and reform. The old myths, heroes crossing oceans, explorers scaling mountains, would pale next to the epic of Earth's exodus. Future Homers might sing of engineers who bent gravity itself, while dystopian tales warn of rogue AIs steering us into black holes. Religions could sprout around the ship's navigators, their calculations revered as divine scripture. Children's lullabies would encode star maps, ensuring even the youngest never forget the way back. And memoirists stranded between cultures would pen chronicles of the displaced generation, those who remember sunlight filtered through the Milky Way's dust, now fading into legend. Visual art would explode in scale and medium. Orbital projectors might etch light sculptures across Earth's atmosphere, visible for generations, a fleeting monument to our passage. Tattoo artists could ink bioluminescent constellations that shift with the wearer's pulse, mirroring real-time star movements. Underground galleries might house fragile pieces made from ice harvested from the Oort cloud, melting slowly under artificial suns as a metaphor for impermanence. The very definition of landscape would warp. How do you paint horizons when your world is a sealed arc adrift in nothingness? Language itself would mutate. Words like sunrise or season might linger as archaic poetry, their meanings hollowed by new realities. Slang would bloom around the journey's rhythms, phrases like riding the warp for taking risks or eating starlight for enduring hardship. Entire dialects could emerge among crews maintaining the planet's thrusters, their jargon unintelligible to surface dwellers, and humor, that vital release valve, would turn dark and absurd. Jokes about failed course corrections or betting pools on which star will hit next. Yet the most profound change would be inward. Human identity has always been tied to place, to rivers, mountains, hometown streets. Uprooted from cosmic context, we become something new, a species defined not by where we are, but by where we're going. The art we create, the stories we tell, even the way we love would bear the weight and wonder of knowing home is no longer a dot on the map. It's the fragile world cupped in our hands, carried like a lantern into the dark. Every precaution taken in moving Earth would carry an underlying terror, the thin line between salvation and apocalypse. Imagine the thrusters misfiring during acceleration, ripping tectonic plates apart like wet paper. The very forces meant to propel us could liquefy the crust, sending tsunamis of magma surging through continental shelves. Or worse, an error in gravitational calculations sends Earth veering into a rogue black hole, where tidal forces stretch mountains into strands of molten rock before the planet snaps like a twig. These aren't abstract fears, they're fractures in the fragile shell keeping humanity alive. Stranded scenarios haunt the margins of possibility. A power failure in mid-transit could leave Earth drifting in the abyss, its artificial suns flickering out one by one. Temperatures would plunge to near absolute zero, freezing the atmosphere itself into a snowfall of nitrogen and oxygen. Without energy to maintain magnetic shields, cosmic rays would bombard the surface, sterilizing what little life remained. Generations born in this slow death might adapt, living in geothermal vaults, harvesting heat from radioactive decay, but their world would shrink to a guttering candle in the dark. Collisions pose existential stakes. A misfired slingshot around a neutron star could hurl Earth into a catastrophic rendezvous with another planet or a wandering brown dwarf. The impact energy would vaporize oceans, shatter continents, and reduce the biosphere to superheated plasma. Even near misses could strip away the atmosphere like tissue paper, leaving the surface exposed to solar winds and micrometeorite storms. Early warning systems would need to spot threats light years away, with contingency plans to adjust course using fractions of a percent of remaining fuel. Prevention hinges on redundant systems layered like a Russian nesting doll. Planetary-scale shock absorbers, perhaps networks of underground gyroscopes, could dampen tectonic stress during acceleration. Distributed fusion reactors buried deep in stable bedrock might ensure no single failure kills all power. And for collisions, an armada of autonomous drones could deploy instant kinetic deflectors, vaporizing debris with lasers or nudging them away with calculated gravity tethers. The key isn't just engineering robustness, it's anticipating chain reactions where one glitch cascades into systemic collapse. Survival in failure's aftermath demands even grimmer ingenuity. If Earth fractures, Ark ships might salvage fragments of the biosphere, preserving ecosystems in rotating habitats. Stranded crews could attempt a Hail Mary revival, triggering controlled supervolcano eruptions to thaw frozen atmospheres, or mining comets for water to jumpstart hydrospheres. The darkest contingency, uploading human consciousness into radiation-hardened AI matrices, continuing the species as digital ghosts orbiting a dead world. Yet the greatest safeguard isn't technology, it's humility. Moving Earth requires accepting that some risks can't be eliminated, only mitigated. Catastrophe might arrive not as a single calamity, but as the slow accumulation of tiny errors across millennia. The antidote is vigilance woven into culture itself, education systems that prize long-term thinking, governance structures resistant to short-sightedness, and a collective ethos where every decision weighs survival against the void. Because when your home is adrift between galaxies, there are no second chances, only the relentless calculus of momentum and hope. Moving Earth might be the ultimate flex of cosmic engineering, but is it overkill when simpler alternatives exist? Picture this: instead of uprooting an entire planet, humanity constructs colossal ark ships, each housing millions in self-sustaining habitats. These wouldn't be the cramped vessels of sci-fi tropes, but floating continents with artificial biospheres, powered by fusion reactors and shielded by magnetic fields strong enough to deflect gamma rays. Generation after generation would live and die aboard these megaships, their descendants eventually reaching a new star system to terraform fresh worlds. The appeal is obvious: why move mountains when you can just pack your bags? But arks come with their own nightmares. Even the largest ships would pale next to Earth's vast ecosystems. Replicating the complexity of rainforests, ocean currents, or microbial soil networks in a sealed habitat is like trying to cram an orchestra into a kazoo, possible in theory, but a hollow imitation. Then there's the psychological toll. Studies on Antarctic researchers and submarine crews show isolation breeds depression, aggression, and irrational behavior. Now stretch that over centuries in a metal womb where outside means certain death and the risk of societal collapse skyrockets. A single system's failure, a cracked hull, a failed crop rotation, could doom everyone aboard, whereas Earth offers redundancy on a planetary scale. Then there's the digital option, uploading human consciousness into quantum computers, launching our minds toward the stars as streams of data. No fragile bodies, no life support, just pure information riding laser beams to new worlds where synthetic bodies or terraforming drones await. It's the ultimate weight loss program, shedding biology itself. The energy savings alone are staggering. Moving terabytes of data across light years requires a fraction of the power needed to push 5 septillion kilograms of rock. Yet digitization unravels uncomfortable questions. Are we still human if our thoughts run on silicon? Can uploaded minds truly experience a sunrise or just simulate the memory of one? And what happens when cosmic rays corrupt the data mid-transit, leaving fragmented versions of personalities to reboot in an alien server? The horror isn't just technical, it's existential. Planet Moving, for all its absurd scale, sidesteps these dilemmas. Earth isn't just real estate. It's a living museum of 4 billion years of evolution, a masterpiece we'd spend millennia trying to replicate artificially. Every alternative forces a trade-off between feasibility and authenticity. Arks sacrifice biodiversity for mobility. Digitization trades flesh for efficiency. Moving Earth preserves the messy, glorious totality of life as we know it, at the cost of tackling physics at its most unforgiving. The choice ultimately reflects what we value most. Are we clinging to soil and seasons, or embracing our role as a species unshackled from worlds? Neither answer is wrong, but both reveal a truth. Survival isn't just about endurance, it's about deciding what's worth enduring for. Science fiction has been wrestling with the idea of planetary relocation for decades, offering glimpses of both its grandeur and its folly. Take The Hitchhiker's Guide to the Galaxy, where the bureaucratic Vogons demolish Earth to make way for a hyperspace bypass, a darkly comedic take on cosmic indifference. The absurdity hits close to home. In reality, moving Earth would render us just as vulnerable to forces beyond our control, whether bureaucratic error or miscalculated trajectories. Douglas Adams' satire reminds us that even the most audacious engineering projects can collapse under their own hubris, a cautionary tale wrapped in levity. Then there's Interstellar, where humanity's survival hinges on abandoning Earth entirely. The film's haunting dust bowls and dying crops paint a visceral picture of a planet pushed past its limits, making the case for escape over restoration. But it also glosses over the physics nightmares of relocating an entire biosphere. The movie's wormhole shortcut is a narrative band-aid handy for storytelling, but light years removed from the grueling reality of crossing intergalactic space. Fans of the film might dream of folding spacetime like a map, but the truth is messier. Wormholes, if they exist, would likely crush anything entering them with tidal forces or snap shut unpredictably. Games like Mass Effect flirt with similar themes, where ancient civilizations move stars to create relays for faster travel. The tech is sleek, the scale epic, but it sidesteps the gritty logistics of planetary upheaval. Players don't fret over tectonic stability or atmospheric loss when jumping between systems. They just press a button and arrive. This simplification isn't just gameplay convenience, it reflects our collective desire for clean solutions to messy problems. Reality offers no such shortcuts. Even Doctor Who's time-tossing escapades reveal a telling bias. The TARDIS can whisk planets across the universe, but the stories focus on the drama of displacement, not the mechanics. When the Doctor moves Earth to evade the Daleks, the emotional weight lies in humanity's confusion, not the physics. It's a reminder that pop culture often prioritizes the why over the how, leaving audiences inspired but misinformed. These stories share a common thread. They use planetary relocation as a metaphor for resilience, hubris, or adventure, sanding down the jagged edges of actual science. They inspire by making the impossible feel within reach, yet they also risk blinding us to the monstrous complexity beneath the spectacle. The lesson isn't to dismiss them, but to temper their wonder with the humility of real-world constraints. After all, fiction gives us stars in our eyes, but physics demands we keep our feet on the ground, even if that ground is hurtling toward another galaxy. Humanity has never been a monolith where some see bold necessity, others see reckless gamble. The moment leaders propose moving Earth, the planet would fracture along ideological lines, not borders. Picture scientists demonstrating with holographic models of planetary thrusters, while protesters chain themselves to ancient forests, fearing the disruption of ecosystems their ancestors tended for millennia. The scale of resistance wouldn't just mirror past upheavals, it could dwarf them. When the Industrial Revolution transformed societies, dissenters smashed mechanized looms to protect livelihoods. Imagine the backlash when the machine in question is the entire planet. History offers eerie parallels. The colonization of the Americas saw thousands willingly board ships for unknown futures, while others clung to familiar shores despite famine or persecution. Moving Earth would force a similar choice on a cosmic scale: risk annihilation by staying or gamble on an untested voyage. Yet, unlike historical migrations, there's no promised land, just calculations and probabilities. Fear of the unknown could paralyze whole nations. Surveys might show urban populations already detached from natural rhythms, embracing the idea, while indigenous communities, whose cosmologies tie identity to specific stars, reject it as existential erasure. The divide wouldn't be rich versus poor, but rooted versus rootless. Then there's the tyranny of timelines. Construction alone could span generations, demanding taxes and labor from people who'll never live to see launch. Modern infrastructure projects like highways or dams spark backlash over far lesser disruptions, now amplify that to global seismic retrofitting or ocean draining for thruster installations. Legal battles would erupt. Would courts allow eminent domain on continental scales? Could a single nation veto the project, trapping humanity against its will? The political fractures might prove deadlier than technical hurdles. Even if 99% agreed, the 1% dissenters could wield devastating power. Sabotage becomes apocalyptic when targeting planet-scale engines. A single act of ecotourism, disabling a gravity stabilizer or hacking navigation systems, could kill billions. Conversely, authorities might impose draconian measures, mandatory relocations, thought policing disguised as unity edicts, or exile for dissenters. The moral cost of consensus could stain humanity's legacy before we even leave orbit. Yet opposition might lack the luxury of time. If the sun's death throes or an inbound gamma ray burst force the decision, resistance could collapse under impending doom. Crisis has a way of silencing debate. When the asteroid looms, everyone digs shelters. But without an immediate threat, the debate could tear societies apart, pitting grand visions of destiny against the visceral terror of uprooting everything alive. The most haunting question isn't whether humanity would unite, but whether unity is even possible, or if moving Earth would require leaving some behind. The silence of the cosmos gnaws at this grand ambition. If moving planets is within reach of an advanced civilization, why does the universe appear so still? The Fermi paradox, the glaring absence of any observable alien activity, hangs over this entire endeavor like a shadow. Enrico Fermi's famous question echoes here with renewed force. Where is everybody? If other species have mastered stellar engineering, why aren't galaxies littered with the relics of relocated worlds or the glow of Dyson spheres? The eerie emptiness might imply that planet moving isn't just difficult, it could be a lethal mirage, a technological dead end that civilizations reach only to vanish. One chilling possibility is that civilizations capable of such feats don't survive them. The Great Filter hypothesis suggests some insurmountable barrier lies between intelligence and galactic-scale engineering. Perhaps the very act of harnessing such power invites self-destruction. Imagine a species that unlocks the energy to move planets, only to weaponize it in cosmic wars, leaving behind nothing but irradiated debris. Or worse, the technology itself might be inherently unstable, like trying to control a star's fusion with sticks and stones. A single miscalculation could rip a planet apart, turning a triumph of engineering into a tombstone. The silence of the universe might not mean we're alone, just that no one survives their first steps into this realm. Yet absence of evidence isn't evidence of absence. Advanced civilizations might have moved their worlds in ways we can't yet detect. A relocated planet nestled in the habitable zone of a quiet star could blend seamlessly into the cosmic background. Or perhaps they've transitioned beyond physical substrates entirely, uploading into quantum matrices where planets are irrelevant. The universe could be teeming with life that's simply unrecognizable, not in ships or megastructures, but in whispers of dark matter or encoded pulses in pulsar beams. Our telescopes are tuned for biology and engineering as we know them, but what if the truth operates on rules we haven't dreamed of, the darkest interpretation? We are alone. Earth might be a freak accident in a sterile cosmos, life's flame flickering briefly before the wind of entropy snuffs it out. The sheer improbability of our existence, the precise balance of plate tectonics, atmospheric composition, and stellar stability, could mean no one else has ever beaten these odds. In that case, moving Earth isn't just an engineering challenge. It's a Hail Mary pass tossed into the void, our only chance to keep the spark of consciousness alive in an indifferent universe. But here's the twist: the Fermi paradox might be our most valuable clue. If no one else has moved planets, perhaps it's not because they failed, but because they found better solutions. Maybe civilizations mature to a point where planetary relocation seems quaint, like building a steamship to cross an ocean when airplanes exist. The absence of megastructures could signal not extinction but transcendence. The universe's silence might not be a warning, it could be an invitation to think differently. After all, if we're asking the wrong questions, the answers won't matter. The real test isn't whether we can move Earth, but whether we're brave enough to question why we'd need to in the first place. 1 billion years from now, if humanity succeeds in moving Earth across the cosmos, our story might not be written in books or etched in stone. It could be woven into the fabric of the universe itself. Imagine future civilizations gazing at the night sky, finding our planet orbiting an alien sun, its journey preserved in astronomical records like a fossilized footprint in the sands of time. Would they see us as pioneers or cautionary tales? The sheer audacity of relocating an entire world could elevate humanity's legacy to near mythic status, a saga passed down through epochs, warped by retellings until the line between history and legend blurs beyond recognition. Consider how ancient myths distort real events over centuries. The floods that shaped early civilizations became the story of Noah's Ark. Volcanic eruptions birthed tales of gods hurling fire from the heavens. Now amplify that over 1 billion years, Earth's migration might morph into a cosmic exodus narrative, perhaps a parable of escape from a dying god star, or a celestial rebellion against the tyranny of gravity itself. Future historians could debate whether we were fleeing annihilation or chasing divinity, our true motives lost to the erosion of millennia. Even the technology we used might be reinterpreted, thrusters becoming sky chariots, gravitational slingshots recast as the hands of unseen giants. The harder the science, the softer its edges become in memory, yet some traces might endure with eerie precision. Deep beneath Earth's crust or buried in lunar archives, time capsules could survive nanoscale etchings on diamond plates, quantum-encoded data vaults, even self-repairing AI chroniclers designed to awaken when new civilizations arise. These wouldn't just record facts, they'd preserve context, the desperation of a species facing stellar doom, the ethical quarrels over who got to steer, the bittersweet farewell to the Milky Way's familiar constellations. Future explorers might uncover these relics and experience our era not as distant prehistory, but as a visceral, emotional echo across time, the darker possibility. Oblivion, space is merciless to even the mightiest monuments. Over geological timescales, mountains crumble and continents shift. Synthetic megastructures would fare no better. Earth's thruster mounts could erode into unrecognizable mounds, our shield generators melted to slag by eons of cosmic rays. Without caretakers, the very evidence of our feat might vanish, leaving only anomalies. A planet improbably far from its star's birth cluster, isotopic signatures hinting at ancient energy manipulation. Future astronomers might dismiss Earth as a cosmic oddity, never guessing it was piloted there by hands now dust. But legacy isn't just about physical remnants, it's about influence. If humanity's gamble sparks an interstellar diaspora, with Earth as the prototype for mobile worlds, our descendants could spread this technology like a cosmic seed. Imagine fleets of worlds navigating the void, their cultures rooted in the original exodus, their languages carrying fragments of ours like linguistic fossils. Alternatively, Earth might become a warning, a monument to overreach. Civilizations that stumble upon our story could see it as a boundary not to cross, proof that some forces should remain untampered. The most haunting question isn't whether we'll be remembered, but how we'll be judged. Will future minds admire our courage or scorn our arrogance? A species that moves planets is either the universe's greatest stewards or its most reckless children. The answer, like our journey, won't be found in the stars, it's written in what we become along the way. What does it mean to hold the fate of a planet in your hands? The scale of moving Earth defies comprehension, a dance of forces that shape galaxies, harnessed by a species barely out of its cosmic infancy. We've mapped the obstacles, the energy demands dwarfing all human achievement, the fragility of ecosystems stretched across interstellar voids, the generational toll of a journey longer than civilization itself. Yet for every answer, 10 new questions emerge. Can gravity be tamed without ripping continents apart? Will human identity survive the loss of familiar skies? And perhaps most haunting, if other civilizations faced this crossroads, why does the universe whisper no clues of their passage? The audacity of this endeavor reflects humanity's dual nature, equal parts engineer and poet. We're creatures who carve equations into blackboards while dreaming of oceans on distant moons. That same restless spirit built cities where there was desert, split the atom to light homes, then turned those tools toward the stars. Moving Earth isn't just physics, it's philosophy made manifest, the ultimate test of whether intelligence can outthink the universe's indifference. The challenges are cosmic, but so is the vision, not just to flee a dying cradle, but to carry it with us like an heirloom into the unknown. Yet ambition must dance with humility. For all our calculations, we can't predict how Earth's biosphere, that delicate membrane of life, will weather an odyssey no evolution prepared it for. Nor can we know if the Milky Way's quiet corner was life's only sanctuary, or if stepping beyond its borders invites perils beyond comprehension. The weight of this choice lingers like a held breath. Do we gamble on becoming galactic nomads, or pour that same ingenuity into stretching our home galaxy's lifespan? Both paths demand brilliance, both whisper temptations of hubris. So let's leave the final question hanging in the air, as vast as the voids between galaxies. Is our destiny written in the soil beneath our feet, or in the starlight yet untouched? The answer may define not just humanity's future, but what it means to be a civilization worthy of the cosmos. Look up tonight, those pinpricks of light could be waypoints or warnings. The choice, like the stars themselves, awaits.